if you pretend that you're like squashing a bug, you can kind of feel where that hip joint is working.
I'm bionic.
Okay, yeah.
It feels like someone's guiding me to teach me how to like do a model catwalk. It's very like it's very hip heavy. Oh,
building an intelligent model or controller that really understand user intent, I think is the huge bottleneck. Unfortunately, a lot of the labs in our field, I think they're doing things wrong.
Today, we're flying to Pittsburgh to meet Carnegie Mellon Robotics Professor Inseung Kang to check out the capabilities and challenges of AI-driven wearable exoskeletons. Professor Kang's work combines machine learning, robotics, biomechanics, and wearables engineering to enhance human mobility.
Okay, so you have to do one arm there, and then the other arm. Okay, yeah, so I'll position this, and then you'll try to just get it to sit on your hip joint. So if you pretend that you're like squashing a bug, you can kind of feel where that hip joint is working. I'll kind of give this to you, and then you can kind of do the belt first, and then
just put this at the hip?
Yeah, yeah.
Okay.
And then we can adjust it if we need to. Loosely strap those ones, and then you can do some motions, some squats, and see how if it restricts your motion at all.
Yeah.
And we can adjust them. Do it loose first, and then you can kind of see how it feels, and we can adjust it after that.
It's a little restrictive at the end here.
Yeah. Okay. So maybe I think I'll push it down just a little bit. Let's see.
Okay.
Yeah,
there we go. Yeah.
Okay. Yeah. Once that feels good, then we'll make them super tight.
Okay.
These are like just 2 set pelvis. So this one. That one's just to distribute the pressure, and then this one is to keep it nice and
I appreciate that this is slimming because I'm not as fit as I used to be.
Yeah, that's really the goal of that. Perfect.
I'm bionic.
Like,
Are you a robot now?
do you have the code in your folder? Okay, yeah. We can oh wait, sorry.
I like that it hides the belly. Whoever designed these straps is actually super considerate, you know, like it hides all of the parts where men store fat. Wow, this is so exciting.
What is your weight?
Oh! So yeah, this is our, like we call it like a biotorque controller. So it's using the onboard sensing to try to estimate what your hip joint is doing, and then it's applying some scaled down and delayed version of that. As you try to slow down, IMU values will get smaller, and then so now it will start to inference, okay, you're doing like less torque or you're moving less in your range of motion.
Exostar 3, 2, 1.
Okay. And then yeah, you have that red button by your chest, so if it feels uncomfortable, you can press that.
Oh, okay.
Can you feel it?
Yeah, I'm starting to feel it. That's cool. Whoa. It feels like someone's guiding me to teach me how to like do a model catwalk. It's very it's very hip heavy. You know, I feel like I'm being taught to shake it.
Yeah.
You know what I mean?
Sassy.
So right now it is only giving 10% of your body generated torque. So it estimates how much torque your body generated, and then we are only assisting 10% of it.
What's the maximum amount of assist?
Maximum this motor can apply 18 Newton meter, considering your weight, and probably 18% will be the max for you.
Just 18%?
Yeah.
Oh, okay.
Yeah, we can do that. All right, I'll stop the treadmill.
This could be a little bit very abrupt to your body.
Okay, that's fine.
Exo on.
Okay, starting treadmill.
Whoa.
Oh, sorry, that is the wrong direction. That's my bad.
It feels like someone is humping me from behind.
So it could be not good for your.
You can try like 15.
Maybe this isn't strapped tight enough.
I mean, right now your hip and the actuator is not aligned.
Oh.
Yeah, do you need the difference?
Because for everybody we have to change the.
Okay. I see. That's like a 1.5 inch misaligned.
Okay, Exo on.
Starting treadmill in 3, 2, 1.
Max power, right?
Yeah, try to.
Oh, yeah. It's really weird because if I try to like not do anything, it feels like my legs are walking on their own.
Yeah, isn't that funny?
Yeah.
Like walking for you.
You can actually do something like squat, then you can feel how it works.
Oh! What?
Do you feel
Yeah.
it like boosts you up?
Yeah, it was I feel the assist, but more so I feel the ridge digging into my lower back.
I know, it's
About the
padding back there.
interface problems.
Yeah. Oh, that was awesome.
Yeah, you can wear the knee one as well if you want to try that.
Yeah,
Oh,
so,
yeah.
yeah, so
Amazing.
we went through like 3 different iterations. One of the main things kind of with this project that we wanted to do was, in the exoskeleton field, it's like, trying to have a one-size-fits-all is very hard. We made like custom strapping to kind of like help with like ratcheting it to different people. But don't make it too tight yet, because we want to make sure it like sits well on where your knee is.
Yeah.
Always like the joint and actuator axial match is very important.
So you got to stand up for me and then just like kind of bend your knee.
Oh, wait.
We'll get it
Am I
in place.
imagining that it...
Probably imagining.
It's because there's some weight on it. Yeah.
Magical.
Those kinds of things.
That's really cool.
At least you can move like without like move out very naturally. So
Yeah. It doesn't feel impeding at all. That's awesome. Ha.
knee is more of a contributing to the non-cyclical tasks such as jumping or the lunging, whatever, and then ankle and the hip joint contribute to the more cyclical as you're walking or something.
Thank you so much for taking the time, Professor. Will you introduce yourself and how you started on the work that you're doing?
Yeah, so my name is Inseung Kang. I'm an assistant professor in mechanical engineering at Carnegie Mellon University, and I also affiliate with Robotics Institute. And I got started to working in robotics because in undergrad, I was interested in building things. And as I was looking into grad school, I met my PhD advisor, and he convinced that building robots, but for helping people, has a good cause. And I was very interested in mobility problems, and I was good at robotics, so kind of tie these to build the wearable robotics, which I kind of work on now.
What are the biggest challenges you face in building seamless human-machine interfaces?
I think the huge bottleneck is the software side of things. So building exoskeletons has been pretty well studied now. So physical mechanical designs have converged. There's some commonality in terms of design across labs or industry, but building an intelligent model or controller that really understand user intent. And what I mean by user intent is, what is the person trying to do? Is the person trying to sit to stand, or maybe climbing flight of stairs, or just walking level ground? Understanding those and effectively assisting during these dynamic movements, I think, is the huge bottleneck.
How do these machines anticipate or understand these intents?
So mostly on these exoskeletons, there are different onboard sensors, such as inertial measurement units or joint encoders, that really tells you about how your limb is moving in space. And using these, there can be a different approach, but conventionally they use model-based approach, some analytical approach to calculate, let's say, a person's walking speed or a person's range of motions. And then they map these, what we call user state information, into the robot torque control. What I do with this is using AI-based models to understand that this person is doing these different type of activities or different range of motions or speed, and then correctly map this into assistance.
Sensor-wise, what are the other sensor options?
Right now, I've talked about kinematic sensors, so like inertial measurement or encoder for angular velocity or positions. But also people have used different biological signals such as surface electromyography. So these are sensors that you can put it on your skin and that kind of captures your muscle activations, or other type of kinetic signals such as pressure insoles or capacitive sensings, or even ultrasound. But then there's a trade-off between the value it adds by adding more sensors versus the usability of the system. Imagine you're having a person to wear an exoskeleton that requires 50 sensors to be worn to do a certain task. A person might not want to do it because it takes 30 minutes to don these systems.
Hypershell just launched a consumer wearable exoskeleton to help with running and hiking. What are your thoughts on this device?
I think it's definitely a very well-designed device, but one thing that I want to clarify is that Hypershell is not the only company that's in this game, and there are actually very good devices built by other companies. Like there's a company called Skip, which is a spin-off startup from Google X, and they recently partnered with Arc'teryx on making these really well-designed hiking knee exoskeletons. And there's also a company, a startup called We Robotics from Korea, that has a high-functioning hip exoskeleton for elderly individuals. And the underlying models or controllers that's running on these devices are pretty similar. So in terms of novelty of the algorithms or the design itself, I feel like there's not much differences. But one thing that I do give kudos to Hypershell is that they've significantly lowered the cost of these devices. And that really opens entry barrier for average person to purchase these devices, because if you ask someone, this exoskeleton will give you X percentage boost on your performance, but requires you to pay $5,000, then people might ask, is this really even worth it? But a Hypershell is about less than $1,000. So that really is, I think, the huge benefit of this company.
What are the biggest gaps between in-lab research and real-world deployment of a commercial consumer product?
Yeah, I think there's mainly two parts. One is maybe over the last decade, everyone has been working on in-lab setting validation of the device. So they build these cool controllers and robots, but they're really not testing out in the wild, real-world tasks. So they might really try to optimize their controllers or models in a steady state walking on a treadmill. But if you think about what a person may do on a daily task, you don't just walk on steady state locomotion for hours. So really testing dynamic transient task, I think, is going to be needed to really translate this. Another thing is majority of the work, though what they claim is to help individual with motor impairments, 99% of the time, exoskeleton research has really focused on healthy young individuals, meaning that it doesn't really handle individuality of gait. So personalization and thinking about a various patient population and how those gait dynamics change and building a controller around it, I think, is the important factor.
What are some unexpected challenges that you faced while developing these exoskeletons?
One of the key unexpected challenges is that everyone's different. So what I think is good may not be good for the test users. Over the last 10 years or so, everyone in this field has been working on minimizing energy. So energy, thinking of it as like a locomotor objective. What is the objective? What do users want when use these exoskeletons? We think that minimizing energy is the gold standard for locomotion. But there's many other dimensions of locomotor objectives, such as stability, agility, and even preference. So going back to it, what I think is good may not be good for you. So accommodating all these variances of locomotor objective is something that I wasn't aware of, that I think is an important research question that needs to be addressed.
Of these objectives, energy, stability, agility, and preference, how would you rank these in terms of importance for your lab and the focus of your research?
For now, I am mostly focused on stability, just because we have done energy minimization quite a bit as a field. So we have pretty good understanding of how to provide assistance that can minimize energy. But the next big step will be stability. And there's many ways to define stability. But at the end of the day, what I think is an important factor for defining stability is ensuring that people don't fall. And ultimately making a hybrid system where most of the time you'll be energy minimization control, but in the case where perturbation or disturbance happen, these kind of stability enhancing control kicks in. And then once we have a full capture of energy plus stability, then I think the user preference comes in. If a controller is doing what we think is good, but the user don't really like it, then is that the right solution? There's some sweet spot between user preference and global objectives that we want to target that we need to balance. Then I think maybe agility comes in, because agility is often related to healthy young individuals of maximizing locomotor performance. Because what I focus on is patient population, I feel like agility is more on the lower end of priority.
Makes sense. So would a stability optimized exoskeleton be for rehabilitation and walking and to prevent a patient from, say, taking a fall while recovering their locomotor capabilities?
Yeah, so right now we're working with aging populations, so we're working on older adult gait. But I feel like this expands to any type of motor impairments like stroke, Parkinson's, or even children with cerebral palsy.
Moving on to controls questions, how can the exoskeleton anticipate what the user is planning on doing so that the motion feels effortless?
We call this user intent recognition or user state estimation. So most of the time we use either model-based approach or some sort of AI/deep learning-based model to estimate what the person is trying to do. And there's many ways that you can define what the person's trying to do, such as defining walking speed, activity recognition. What's mostly done recently is directly estimating the physiological state of the user, such as what is the joint movement, what is the muscle activation, what is the force the person is generating. And we often use onboard sensors, like kinematic sensors like inertial measurement units or encoders, to train these neural networks that can estimate a person's state in real time.
In the device, how does it know to stop a motion? Say you're picking up your leg, how does it know where your motion should end and when to reverse the motor assist?
Maybe over the last 10 years, everyone has kind of developed these robot controllers in a hierarchical manner, meaning that you make a model that can estimate walking speed, you make a model that can do activity recognitions, and then you do almost like a lookup table based on the combination of these different state estimation. So if you want to make sure that the assistant stops when person is not moving, if you want to do it on a stair assistant, ramp assistant, level ground assistant, you have to infinitely figure out the discretized classes of movements. And it's not feasible because there's infinite number of combination of daily activities. So a recent kind of research direction is directly estimating physiological state. And if you directly estimate these physiology, then what enables us to do is if the person doesn't move, their underlying physiology doesn't change, meaning that the exoskeleton will automatically go to 0 torque. Versus if you start moving, regardless of whatever activities, it will automatically scale proportional to your biological demand. So imagine a true volitional control. If you're doing squatting motion, it gives you squat motion. If you do sit to stand or jump, it gives you the corresponding assistance.
How do you deal with unpredictable movements, like a sudden fall, and anticipate and correct or support recovering from that fall?
We don't have an existing controller that can accommodate fall. So hence we're working on stability enhancing control so that it doesn't lead to fall. But that's definitely an active area of research we want to expand because it is possible that even with our exoskeleton, the individual can still fall down. But one thing that I want to mention is the robot only does partial assistance. So a human can actually still override and complete a motion that can lead to potentially a fall.
So if it doesn't anticipate well, the fall could actually be worse with the device.
Yes.
Yeah. On this similar note, we've seen videos of humanoid robots flailing about violently. How do you design a controller that can gracefully handle these unexpected sensor failures or other variables?
Yeah, that's a great question. Unfortunately, a lot of the labs in our field, I think they're doing things wrong because they're training these models or creating these designs or controllers based on physically collected data. You just talked about humanoid falling. This means that in order to create a model that can help individual with motor impairments to fall, this means that you're going to recruit subjects who are stroke survivors or older adults and have them come into the lab and have them fall many, many times. I just don't think that's feasible. So in our lab, we mostly utilize computer simulations to simulate different fall incidents and using these synthetic data to train a model without actually doing these exhaustive data collection of human fallings. I think the approach-wise is very similar to how humanoids are being trained, simulating different falls of hundreds of thousands of cases in simulation and making a control policy that we can deploy to the robot.
In those simulations where you're generating artificial fall data or fall scenarios, how do you first create that model and then how do you bridge the sim-to-real gap?
There are two ways to go about doing it, and we're exploring both options. One is doing completely data agnostic way. So these simulation pipeline has musculoskeletal human agent. So it has the same body structure, morphologies that mimics human body. And we use complete data agnostic reinforcement learning way to train these agents to learn to walk. And then once we have a walking agent, then we put an exoskeleton in simulation and train these controllers. Another approach is imitation learning. So we leverage some small portion of actual user data that can be collected through a motion capture settings or through a video image, and then use this data as a reference trajectory for these agents to learn and mimic gait. And then once you have the trained agent, you do the similar approach of representing an exoskeleton model and then train a controller around it. The sim-to-real gap is much greater on human-robot interaction type of research compared to quadrupedal or humanoid robots because there's humans involved in this scenario. So just because you can represent human walking in simulation doesn't mean that we can completely map how humans will respond to these exoskeleton assistants. Even if we think that assistants do some XYZ performance in simulation, an actual person in an experimental settings, they may do completely different behavior. So we don't think there is going to be a zero-shot transfer of these controllers from simulation to real world. But we do think that whatever controller that we build in simulation will give a good initial guess or seed to the experimental validation.
Gotcha. So with the massive variation in the musculature and stature of the population, would this model be optimized for the average size, or are you able to tune or adapt the model for variations in human height and stature?
Yeah, that's a great question because there's concept of skeletal model and there's a concept of musculoskeletal model. So if you only work in the skeletal model, which basically only works at the joint space, then you're treating human body as very similar to a humanoid, which is not the case if you think about patient population because of the muscular dystrophy or maybe limited range of motion. There's a lot of factors that alters their gait patterns. Using these musculoskeletal simulation, now we can create some muscle tendon dynamics that mimic different patient gait. So imagine if you are working with stroke survivors, then perhaps we limit the muscle activation levels on a distal area, simulating such as foot drop. So we have all these flexibility of changing these different muscle activities to target different patient populations.
Wow. This is sounding like an extremely complex and sophisticated model. Are there limits to the complexity of the model or the computing capability that you guys are running into?
So fortunately, I'm not the one actually building these frameworks. There are companies or research labs that's actually only working on developing these models and simulation pipelines, such as Hi-Fi is one kind of major company on these musculoskeletal simulation. Exosuite is also another huge company that's working on this in this area. And the nice thing is most of these are leverage GPUs type of setting for parallelized operation. So it can really expedite the computing cost. One thing that I think is the huge bottleneck is the cursive dimensionality in terms of the action space. So because there are so many different muscles, at least the model that we're working with has 90 muscles to drive limited number of joints, that there's multiple redundant combination that results in the same motion. So training these learning-based agent is extremely hard if you think about all the possible combination of these muscle actions. What we do is kind of mapping these 90 muscles into more latent space or reduced order of action space. Right now we're working with 12 action spaces. In the biomechanics or neuromechanics literature, we call these muscle synergies. So there's a reduced order activation that leads to higher order muscle activations. And if we carefully curate these models, now we're only working with 12 dimensions to control the full lower limb 90 muscles.
With the AI-driven motor control, how do you ensure user safety?
Yeah, that's a great question because it always comes back from the review comment on how do you guarantee that this is actually safe for the user? And the answer is honestly not, because at the end of the day, ML or any AI model is a statistical approach to control these robots. So there's no such thing as 100% guarantee. Of course, we do have multi-layers of safeguards to make sure that if some anomaly happens on these model estimates, then it constrains the actions. Also, there's physical hard limits to these robots that ensures that the joint doesn't go outside the range of the human motions. And another thing is that these robots are partial assistants. So it only provides about 20% of your biological capacity. So a person can easily override. This is a bigger problem in the field of robotic prosthesis, where the robot leg completely overrides your full action. So these guarantees or safety can really be more detrimental in these robots' controls.
Now shifting onto some biomechanics and motor control questions, is there any risk of people becoming dependent on this or altering their neuromuscular control with prolonged use of this kind of device?
There are some biomechanics literature start to look into longitudinal effect of using exoskeletons, and it does change their underlying joint mechanics. The question of whether that's good or bad is still unanswered, but it is definitely a new area or avenue that people are working on.
What role should the exoskeleton play in stability and in physical rehabilitation?
I don't see people wearing these robots 24/7 unless they have a physical dependency. Meaning that if your physical capability enhances using these exoskeletons and you don't need to use exoskeletons, I don't want them to use exoskeletons. Ultimate goal is that these robots promote and has some retention of enhanced capabilities that people can do things that they couldn't do. But there are definitely populations that will depend on using these robots to do things that they couldn't do. But ultimately, we should start looking at how do we ensure that whatever the gait enhancement that we learned from using exoskeletons, how do we make sure that it stays with you? Should be a whole new area of research.
Interesting, yes, like a teaching device.
Yes.
What metrics would you use to assess the successfulness of your research or this human-machine integration?
So right now I'm looking at a very standard biomechanical measures, such as inverse kinematics and dynamics to look at joint work, joint mechanics, muscle activations, and metabolic cost. But I feel like we need to integrate clinically adopted metrics, such as time up and go, or there's some clinical testings of a Borg test and other ways, depending on the population, that's commonly adopted in the clinical settings. So hybrid of those. And then lastly, along with that user preference, I think will enable more multi-perspective way to understand how good this device is.
What, if any, would be the ideal sensor that you would wish for the optimal predictive control?
I think there are enough sensing modalities that's available in our research settings. I think the bigger question is how do we distill everything into a more compact, low profile, easy to use form factor? So imagine you have access to inertial measurement unit, muscle activities, ultrasounds, joint encoders, but all in a very streamlined, low-profile form factors. Right now, not that I know of, there's not an existing solution. That means the user needs to wear 50 sensors to have access to all these sensing modalities, which is infeasible for a commercial device.
If there was a massive breakthrough in the fidelity of a certain sensor type, like a muscular EMG or a brain-computer interface, would that enable you to only use that kind of sensor and vastly simplify the kind of sensing suite that you would allow?
Yes, that will extremely simplify the underlying controllers because now we have direct information to the user's true intent instead of having some intermediate module to understand the proxy of user intent, which is what we're working on right now. Usability, the durability, and even the question of can we wash these sensors at home and still work reliably? Or if I wear this sensor for 12 hours, will it have some degradation in performance? These are some practical questions that needs to be answered for a commercial device.
In a magical scenario, what is the perfect super sensor that you would use for this?
So I am a huge believer of neural interface, which is not the topic that I work on, but companies like Neuralink, I think, is doing some good work on looking at the cortical activities and try to utilize those brain signals to control robots. And I feel like ultimately we would have access to what's happening at the brain level, what's happening at the spine level, and what's happening at the muscle level directly so that we can kind of close the loop with our wearable robots.
What advice would you give to someone interested in wearable exoskeletons?
I think this is an exciting field. We had a GPT moment recently of having a breakthrough of AI that now an average person down the street knows how to use a GPT. And now we're just getting to start picking up on the robotics field. You see a lot of media coverage on humanoid robots or quadrupedal robots. Maybe in the next 5-10 years, we'll have the next GPT moment in the wearable robotics because using these robotics technology for human mobility is a no-brainer.
So your background is in mechanical engineering, correct?
Yes.
Can you Walk us through how you shifted from traditional mechanical engineering to all of this biomechanics, full suite ML controls space?
I think not just my field, but any type of research field is nowadays non-traditional. So it's highly interdisciplinary, and you can't just go off of textbook knowledge to create something new. It just came natural for me to learn things that wasn't taught in undergraduate courses. So I had to learn physiology, anatomy, biomechanics, neuromechanics, and conventional controls and robotics and whatnot. For people who want to get into this field, the best starting point is just being open to accepting different new technologies or areas of research.
Would you say there's any pivotal moment or big lever for your change and your growth into this field?
Yeah, I think the biggest pivoting point was as I was entering graduate school and meeting my PhD advisor. I wanted to immediately see my technology happen and giving impact to the society. And I feel like healthcare is a big area that we can make an impact. So I wanted to utilize robotics technology that I was good at, but using for the goods of people.
What would you say is the biggest missing piece for the next big breakthrough in wearable exoskeletons and robotics?
There needs to be a bigger push in the industry. Right now, there are a few startups, but I think it's just not enough momentum to really drive this field, to do a translational research, multi-site, cross-studies, and whatnot. Single lab can only do work at a single lab level. And I think similar to how robotics are now being led by industries with big players, kind of big tech companies playing a role, should be done in this field as well.
So in your vision, what will exoskeletons look like in 5 or 10 years?
My ultimate vision is that we will have exoskeleton and clinician closed loop, where automatically, whether that's through wearable sensings or computer visions, you just do your daily activities and we can use AI models to understand your gait pathologies or some neurological damage and whatnot, and preemptively suggest to your clinicians that this user may experience some injury or some motor impairment, so we need to provide some prescribed solution of using exoskeletons. So imagine your Google Calendar already booked an appointment with a clinician next week to do some exoskeleton studies, that you go to the clinical settings and it's already optimized or adapted or personalized to you, that in a matter of few hours in a clinical settings, then come back and you're now get back on your feet.
Very cool, like full body diagnostics.
Exactly.
Yeah, I think that largely covers it. Is there anything else you'd like to say to the viewers?
My lab is relatively new. It's only been a year and a half, but hopefully in the next 5 or 10 years, we make a good breakthrough in translating these technology outside of the lab. So please look out for my research.
Awesome. Yeah, best of luck. Thank you so much for that.
Yeah. Thank you.
Thank you for your time. If the exoskeleton is around, would it be possible to, like, at a high level, point out the key components?
For sure.
Grab this.
Yeah, so this is a robotic hip exoskeleton. So imagine this is the backpack that you're going to wear, and this is the pelvic interface and thigh interface that wraps around your leg. Typically, an exoskeleton has a few actuators. These are electromechanical actuators that has some gear reduction inside of a motor, and then has some motor drivers in a very compact form. And it generates some torques, and it also measures the joint positions and angular velocities. Pelvic interface that has some width adjustment mechanism that can accommodate different body sizes. These were 3D printed out of nylon, but there's many different materials we've been testing to see if it has good rigidity and robustness to torque transmission. Onboard computers are usually different levels of, depending on what you're trying to do, you can just use a standard microcontroller like Arduino Tinsy, or a microprocessor from like Raspberry Pi, to we use NVIDIA Jetson Nano. I think it's pretty typical for any robotics technology recently. So it's two-tiered, where we have a low-level controller that directly communicates with the motor through a microcontroller, and that microcontroller communicates with onboard microprocessor like NVIDIA Jetson that runs machine learning models. So it kind of has some inference modules. And then we have a few custom printed circuit boards that regulates different voltages or different additional sensor signals. And then here is, imagine this will be attached to your thigh. We add an additional inertial measurement unit on each thigh and then one on the pelvis. So basically, we want to log the kinematics at each limb throughout the space. So right now, this hip exoskeleton at least has 3 IMUs and 2 encoders for sensing, 2 actuator for providing bilateral assistance. This is a knee exoskeleton prototype that we've recently built. A very similar setup, like the actuator is the same. Because this is a prototype, we kind of do it on a breakout board, but these are TINSI microcontroller that communicates with the motor through CAN protocol, DC-DC buck converter to step down the voltage from a LiPo battery to support not just the motor, but also the TINSI at a different voltage level. Inertial measurement unit that's one on thigh and one on shank, so that we have for each limb. These kind of orthotic shells that wraps around your thigh or shank or pelvis. We do it through multiple iterations to see if what's the generic size that fits the individuals. Also, we kind of look at how do we better make a custom straps. We use kind of ratcheting mechanism like a snow boot that you can kind of ratchet this and then unlock to release.
And you guys made this yourself?
Yeah, everything was in-house. I was fortunate to work with my students to kind of create these prototypes.
My understanding is you've tried a Hypershell.
Yes.
But it's hard to take control of the controller. To what extent can you just buy one of those and rip out the compute and then just rewire your package into the motors?
That is definitely one idea that we're currently thinking. We did talk about within the team to reverse engineer the Hypershell to kind of attach our own version of microprocessor onto their motors. But it's a trade-off between what is the benefit we get by testing Hypershell device versus our version of the device. Now, one big difference between Hypershell and this device is the amount of torque we can apply. I believe Hypershell's torque, even though they claim large amount of torque compared to our device, because the interface has been hashed out so much, there's going to be a big mechanical play if you provide large torque. So interface really plays a critical role. So even if you say, I can provide 30 Newton meter of torque, that's at the motor level. Will the person actually realize that 30 Newton meter of torque is all dependent on the interface?
Right. How well and like what those boundary conditions are, or is this just going to dig into your back? Like,
exactly. How well does it anchor to your body is very important. At least what I know is that Hypershell, to minimize the weight extremely, they have to compromise a lot of the anchoring point.
Oh, okay. Is it okay if I leave that in, or is
oh,
that
yeah, sure.
Sick, awesome.
Yeah, they can do whatever, be angry about whatever, because that is my honest opinion. So.
Yeah. All right, thank you so much.
Yeah,
thank
great.
you, Professor.